Hello everyone, welcome to my video lesson in Foundations of Mathematics. I am Miss Monica I. Pinca, a Mami 2 student, and today I will be talking about isomorphisms and homomorphisms, and how we can determine whether two groups are isomorphic or not. Let's get started! Let's have a recap about functions because this could be very helpful in determining whether two groups are isomorphic or not. So when we speak of function, it is a rule or set of rules that translates every element of some group into an element of another group. Let's say we have group A and group B. And we also have a specific type of function that is onto function, which is a function such that every element in B is mapped by some element in A. And this illustration here shows an onto function because as you observe that every element in B is mapped by some element in A. However, this illustration here shows a counterexample of a non-onto function because every element in B is not mapped by some element in A. That's why it is not an onto function. Next, we have one-to-one. That is a function such that no element in B is mapped by more than one element of A. And as you observe that all the elements in A is mapped with every element in B. That's why it is called a one-to-one function. And we also have a function that is one-to-one and onto, and it is called a bijective function. And so, as what our topic isomorphism is all about, it is a bijective function. That is a one-to-one and onto. Next, we have injection. That is a type of function that is one-to-one. Yung one-to-one natin kanina is what we so-called an injection. And the onto function, only the onto function is what we so-called a surjection. And as what I have said a while ago, one-to-one and onto function is what we so-called a bijective function or bijection. Next, so what is an isomorphism? So, to introduce the idea of an isomorphism, I wanted to remind you that sometimes we mean to say the same thing, but we end up using different language. For instance, the three sentences we have here: hello, today is Tuesday in English. Hula, hoy es martes in Spanish. And ula, hoje é terça-feira in Portuguese. Means we're saying the same thing. Now you'll notice that each pair of sentences has the same structure. you have a word for hello in English, hola in Spanish, and ula in Portuguese. You also have today, is, and Tuesday. So the only difference is the language that we use to the individual words in different languages. So in the same way as we talk about isomorphic groups, that is the group with the same form as what isomorphic means but stated in different language. So now we define what an isomorphism is. So an isomorphism phi from a group G to G bar, and that is written as like that. So this is phi from G to G bar is a one-to-one mapping from G onto G bar that preserves the group operation, that is phi of A is equal to phi of A, phi of B for all AB in G. So if there is an isomorphism from G onto G bar, we say that G and G bar are isomorphic, and we write it this way. G is isomorphic to G bar. Next, so one thing to know here is that we're gonna proving that phi of AB, this is phi of AB is equal to phi of A, phi of B, and as you observe that phi of AB, this operation is done in G, and phi of AB and phi of A on this side, phi of A, phi of B is the operation that is done in G bar. Oh, that is G bar. And so it's really important to note that these two groups are different. We have the group G, and we also have group G bar. And this is how operation preservation looks like. So we have an operation in G, and we also have a multiplication operation in G bar, and this is also applied in operation preservation. As likewise, we also have multiplication and addition operation, and it is applied in here, so on and so forth. And next, so these are the steps in proving that two groups are isomorphic. Say for instance, we have group G that is isomorphic to G bar. Number 1, define a candidate for the isomorphism that is defined by phi from G to G bar. Then second one, we're going to prove that phi is a one-to-one, and that is we're going to assume that phi of A, we're going to assume that phi of A is equal to phi of B, and show that A is equal to B. And the third step is we're going to prove that phi is an onto, and that is for every element in G bar Find an element G in G such that phi of G is equals to G bar. And the fourth step is that we're going to prove that phi preserves the operation, and that is to show that phi of AB is equal to phi of A, P of B for all AB in G. And then next, let's have an example. So prove the group of integers under addition is isomorphic to the even integers under addition. And it is written as like that. So group of integer under addition is isomorphic to the even integer under addition. So the first step, or the first proof we have, is to define phi of n is equals to 2n for n in Z. And then the second step is we're going to let mn be the element of an integer. Then we're going to assume that 2m is equals to 2n. And if we're going to divide this into 2, it implies that m is equals to n, and so phi is a 1-to-1. Then for the step 3, for any even integers 2n, there exists n is an element of an integer such that phi of n is equals to 2n, so phi is onto. And then the last step, finally, we have phi of n, phi times m plus n, or phi of m plus n is equals to 2m plus n. And applying the distributive property, we're going to have 2m plus 2m plus 2n, and that is equal to phi of m plus phi of n. And thus phi preserves the operation and is an isomorphism. Next, we are going to show two groups are isomorphic. Let G and J be groups. An isomorphism phi from G to J is a 1-to-1 and onto function. So phi from G to J satisfying phi of AB is equal to phi of A, phi of B for all AB in G. And now we're going to show that a real number under addition is isomorphic to a positive real number under multiplication using the function phi from R to the positive R given by phi of x is equal to 3 to the x. And to do that, we're going to show that phi is a function from R to a positive R, and show that phi is a 1-to-1, and show that phi is a function. I'm going to show that phi of AB is equals to phi of A, phi of B. That is, phi is an operation preserving. And let's do it. So to show that phi of x is equal to 3 to the x maps a real number to a positive real number, we're going to show f maps x to y, pick an arbitrary element x from x, and explain why f of x is guaranteed to belong to y. So here is the proof. Observe that 3 to the x is greater than 0 for all x is an element of a real number. Hence, phi of x maps R to positive R. And then to show that a function x to the y is a one-to-one or an injective function, we're going to show that distinct elements of x are sent to distinct elements of y. That is most commonly done by showing if f of x is equals to if f of x sub 1 is equal to f of x sub 2, then x sub 1 is equal to x sub 2. So suppose that phi of x sub 1 is equals to phi of x sub 2 for x sub 1, x sub 2 is an element of R, that is 3 to the x sub 1 is equals to 3 to the x sub 2, taking the logarithm with base 3 of both sides yields x sub 1 is equals to x sub 2. So phi is a one-to-one. Next, to show that the function x to the y is an onto is an onto function or a surjective function, we're going to show that each element of y is mapped 2 by f. We show that for all y is an element of y, there exists x is an element of x such that f of x is equals to y, which is commonly done by describing which x will produce an arbitrary chosen y. So let y be an arbitrary element of a positive real number. Since y is greater than 0, the quantity log 3 y is a real number. Since phi log 3y is equals to 3 to the log 3y is equals to y, the function phi is onto. And last, we're going to show that a function x to the y is an operation preserving. We're going to show that for all AB is an element of x, it is true that f of AB is equals to f of A, f of B, using the definition and properties of f. So for any real numbers AB, observe that phi of A plus B is equal to 3 to the A plus B, and that is equals to 3 to the A, 3 to the B, equals phi of A, phi of B. And so phi is an operation preserving. So this concludes that the proof phi is an isomorphism because it satisfies all the 4 steps in proving that two groups are isomorphic. And now let's go to a group homomorphism, or in short, a homomorphism. So what is a group homomorphism? A group homomorphism means that we have a function, say for instance f, between two different groups J and H, and f is defined from G to H, and the function f preserves the group operation. Now the question is how a function preserves the group operation. So let's break it down. Let's say G is a group under asterisk and H is a group under star. So you know that these are two different groups which with two different binary operations. The binary operations are asterisk and star. Now we're going to let A, B, and C is an element of G. And F maps to G and H. So A is mapped to F of A, B is mapped to F of B, and C is mapped to F of C. Now if A asterisk B is equal to C and F of A star F of B is equal to F of C, then by substituting the C in here, then we have F of A star F of B is equal to F of A asterisk B, which is exactly the definition of homomorphisms, which preserve the group operation. So, which means that no matter you apply the operation on A and B first, and then apply the function, or you apply the function first, and then the operation, the answers remains the same. So if we have a function between two groups that fulfill this condition, then we say that F is a group homomorphism. Let's have an example. Let's say let a function from the real number under addition to the positive real number under multiplication be the function such that f of x is equal to a to the x. And our goal is to show that f is a homomorphism. So we need to show that f to the x plus y is equal to f of x times f of y. So this is what we're going to show in order to prove that f is a homomorphism. And so we plug in e to the x plus y is equal to e to the x times e to the y by properties of exponents. So f is a homomorphism. And let's have a non-example of a homomorphism. So in here, we can see what a homomorphism wouldn't be. So let f, or let the function of z under addition to the real number under multiplication, where f of x is equal to x plus 1. So recall that f to the f x plus y is equals to f of x times f of y to be a homomorphism. So now we have f, we only have a one counterexample to disprove this, that this is a non-example of a homomorphism. So now we have f to the 1 plus 2. f of 1 plus 2 is equals to f of 3. And then we need to plug in the f of 3 to our function x plus 1, and that would result to 4. But if we plug in 1 to f of x, it could give us the result of 2. And then if we could plug in f of 2 to 2 to f of x, it could result to 3. And then 2 times 3 is equals to 6. And so 4 and 6 is not equal. And so this is an example of a non-homomorphism. Then another example, we have a function of an integer to itself by f of x is equals to 2x, and we have a regular addition for our group operation, and we have a regular addition for a group operation. And so we're going to have, in order to check that it is a homomorphism, we need to show that f of x plus y is equals to f of x plus f of y. From the definition of f, we have f of x plus y is equals to 2 times x plus y. And on the right hand side, f of x is equals to 2x, then f of y is equals to 2y, and so f of x plus f of y is equals to 2x plus 2y, and that is true distributive property. And so we can say that f is a homomorphism. And notice that the output of f is a set of even integers, and the even integers are subgroups of the integer. And to further understand what homomorphisms and isomorphisms are, here is a video. Let's watch this.
In group theory, we can make two completely different groups look similar to each other, or in fact even exactly identical to each other. Let's take two completely different groups, the infinite group of all integers and a finite group containing only two elements, -1 and +1. Since the orders of these two groups are completely different, so it looks like there is absolutely no similarity between these two groups. But the group of all integers can be written as a union of all the odd numbers and all the even numbers. Let's replace all the odd numbers by -1 and all the even numbers by +1. Do you now see a similarity between these two groups? Both these groups contain exactly two distinct numbers, -1 and +1. This is what exactly a homomorphism does. It makes two completely different groups look similar to each other, but only similar, not identical. That's because while the group of integers contains millions of -1s and +1s, the finite group contains only one -1 and one +1. In other words, Homomorphism between two groups ensures that those two groups contain the same elements, but they may not contain the same number of elements. An isomorphism, on the other hand, makes two completely different groups look exactly the same, literally carbon copies of each other. Let's take a look at an example. Let's take these two groups. The group on the left contains 0, 1, 2 and 3, while the group on the right contains 1, I, -1 and -I. Let's replace the element 1 by I to the power 0, the element I by I to the power 1, the element -1 by I to the power 2, and the element -I by I to the power 3. If we ignore all the i's, we end up getting the same elements that we have in the first group. This is exactly what an isomorphism does. It makes two completely different groups look exactly the same. An easy takeaway from this is that for an isomorphism to exist between two groups, those two groups must have the same order. So they must either both be infinite or they must be finite having the same order. One thing common between a homomorphism and an isomorphism is that both these functions map the identity element of the first group to the identity element of the second group. However, in case of a homomorphism, we can have more than one element in the first group that get mapped to the identity element of the second group. But in case of an isomorphism, the identity element of the first group is the only element of the first group that gets mapped to the identity element of the second group. In other words, the kernel of a homomorphism may contain more than one element, but the kernel of an isomorphism contains exactly one element.
And so, to sum this lesson up, an isomorphism is a homomorphism and a bijection. That's all. Thank you.